Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The second talk is by Chiru from ISC, and he asked me to introduce him as just Chiru from ISC.
Good morning, everybody. So first, let me thank the organizers for inviting me to speak. So pardon me for the title. It wouldn't be as boring as what it seems. So we're going to talk about text analytics in a big data setting, and I think the previous talk clearly summed up why, in a nutshell, startups will come up out of analytics and big data, et cetera, right? So this talk, we are going to talk about an interesting problem in text analytics, that of extracting topics from a large document collection. And I was happy to hear the words like unsupervised learning, et cetera. So this would be another example of unsupervised learning. So this is a picture of what? Anybody, any guess? Let's know. I just trying to make sure that you're not asleep. So, yeah, jokingly you can say this is the picture of papers on my desk after the examination. No, I was joking. I scraped it from internet somewhere. So imagine this is a common sight in most of our desks, especially unorganized people like me. So one of us, often one thinks, right, if there was a tool which could help organize these things, in unsupervised fashion, won't it be good, So the main challenge is that the main challenge is, okay, one good thing to organize it, okay, get 10 guys and each of you look at the paper and put it in this bucket, that bucket, right? So that's not possible. You want an automatic scheme, and that's hard. And so there are two reasons, or rather two dimensions of this problem. First of all, what are the methodologies you want to deploy for such a problem? That also we are not very clear. It's an emerging theme. And the methodologies which we currently have are severely challenged if the number of documents are quite large. So what can we do? And this is this is one of, I would say, if a lot of data is in text, and this is today's challenge for sure. So topic models is a very interesting attempt at this problem. So these models attempt to discover hidden themes in document collections. In a minute, we'll try to make this more clear. Now, if you understand the themes in a document, you can use them to label them, automatically tag them, right? And once you have tagged them, then you can use those tags to do, browsing, searching, and storing them efficiently, etc. Right? And these models do not require supervision. So given so many advantages, that is why this has almost, my colleagues in Google and Yahoo tell me that this goes into their backend. I have, except the anecdotal evidence, I can't tell you what's going on there because I don't work there. But this has been now industry standard in organizing large text collections. So just to set some example, just to set some definitions right. So what are topics? So suppose I show you a document on which you see these following words, like run, innings, hit, season, game. Any idea what the document could be?
Baseball.
Sports, baseball, and cricket. So now, if I say the document came out in New York Times. Oh, sorry. So basically, this is, one can say baseball or cricket. If it was Times, it could as well be Times of India, then it would be cricket or whatever, right? So the main idea is that just knowing these few words, you get idea, okay, this could be about cricket or baseball. So that's what you're talking about here, right? So for example, if you run such models, topic models over, say some data set, maybe in this case, you're running a New York Times data set. So obviously you can see the first 5 words of this run, inning, hit, season, game, we talked about it, that's more like baseball. The second one could be, about cooking, and then there is this patient, drug, doctor, cancer, medical. Of course, you're talking about something like healthcare, right? So can you automatically extract them? That is the main idea, sort of, right? So now as you see, these are very interesting and useful things. So people have built some topic models. Here's one great example which I find is advertisement for topic models. I mean, I'm not sure how much of it is used. So imagine Wikipedia, right? I want to browse Wikipedia. So what you can do is you can take the Wikipedia dump, run through topic models. So you can see, I'm not sure if you can read those words. Can you read those things? Household, population, female, family, median, right? So these are the words I'm finding, right? There's another set of words, let's say war, force, army, attack, military, something with military things. Now, so for example, in this particular case, so these are basically some topics you're defining. Topics are now, as I was saying, collection of words now, which appear, co-occur heavily, right? So if you go and click there, you will see the following documents. These are document titles coming up. So this is a great, now you want to say, okay, I've come to a particular document, I want to say related topics, so I can go township, household, population. That defines another topic. So this gives you a very easy way of browsing large document category, just to show one use. But but now effectively all backend search is now driven by these topic models that people from industrial search companies can tell us better. So having convinced you that these are great tools, now let us see how can I learn them, how can I find them. So that's the subject of this talk. So we briefly talked about what are topic models. Now we'll introduce you to a very classic technique called latent semantic indexing, where this is started. And then we'll talk, then if you get time, we'll actually talk about what I mean by learning topics from finite number of sample complexities. This is our recent work with Professor Ravi Kannan and Trapit. So that's the outline. So basically all this started in 1960s, and when the first notion of documents started emerging, document collections. So at that point, people said, okay, I have a collection of documents, and document is a collection of words, etc. I have this model. Now, the main thing is, can I find information? What is information? Now I'll maybe ask a question, and you have to answer this there, right? I'll give you some keywords, and you have to find me the nearest documents. So at that point, the formulation was, I give you a document, find me the closest documents. This was 1970s. So then people then came up with this model, which are called vector space models. So what is it? They said that let's do the following thing. Let us encode in each document the presence or absence of a word. For each document, then I can represent by a vector. And then you look at your query, that also can represent by another vector. Then try to see which documents are closer to that query and return it back to you. This is what I will call as keyword search. Now, very soon, people found that this works sometime, but not always. So if I'm looking for my favorite example is, if I'm looking for something like Jaguar, Jaguar, Jaguar. Now, can you Jaguar the car or Jaguar the animal? Right? It's not very clear, right? Just from that word, right? Then if you say Jaguar adventure, and say Jaguar fast, speed, so this co-occurs helps, right? And then, so sometimes these are not so apparent just by words. One can have, okay, people can write the same word. There are words with same meaning, different words. That can always happen. So all kinds of things came into play, right? So at that point, people came up with this interesting idea that vector space models may not be that good, so they came up with this very interesting idea of latent semantic indexing. And that completely outperformed this keyword search. So let's look at it very quickly to set the tone for this talk. So as we discussed, for us, the data is document collection. We'll encode the data as a matrix, and here is where math comes in. That's what we know. So here, let's assume that each document is a column. I'm sorry to do this in the morning. So each document is a column, and each row in the column is a word. Now, what you fill in the row, it can be depending on what models you have. For example, in vector space model, you can fill in the absence or presence of a word. Or you can count the number of words if you wish, right? Right? So, so for example, let's say that I've counted number of words and divided them by total number of words. So total number of words is 100, and there are 9 words. The first word is say 0.09 and all that, right? So the sum of them should be 1, something like that. We can do other things also, right? So finally, we're given a document matrix. So the corpus are encoded in a matrix A, right? So then people found is that, okay, there is this interesting tool called, from mathematics, linear algebra, called singular value decomposition. What you do is you write this matrix into a factorization, MDS, there are 3 matrices, right? And now, so remember, each column of A is a document, right? So you can see each column written as something like AI into some matrix into SI. But SI, and I'll think about it as a new representation of this document. Okay? So now what I do is now a query word Q is given to me. You know? So what I do is I project the query into this using this MD by this formula, and then I compute a similarity score between Q and AI. Q is the query document and AI is the ith document in my data sets. So now, what I can do is, if this number is high, then AI is close to Q. This is very similar. I'll take this argument. Now I can use this score for each query. I can use this score for all the documents in the corpus and return to you the closest ones. Now this completely outperformed the keyword search. Okay. So now, by keyword search, I mean this Q transpose AI. That is the main thing, if you want, mathematically. So as I said, right? So people are wondering, is this working well? But why? Why should it work well? I mean, what did I do? I mean, just because I know linear algebra, I knew the tool, I ran it. Why? So this was the thing, right? So maybe then maybe the matrix M is encoding something to semantics. Maybe it was projecting, when you say projecting the documents in the columns of M, see there's somewhere the words, so it is not really aligned along each word. It's a direction which is mixing up 2-3 words, right? So maybe this is catching semantic. This is what they're thinking. Yet, see, this is 1998. So people were applying it, using it, no understanding. Now, as you said, 30 years, right? This took 10 years. 10 years later, there's a very interesting paper came up, a classic paper, which tried to explain this. Why does it work? So now, so then said, okay, maybe what we should do, that each document has a notion called topic. We'll define it in a moment, right? So, and if each topic has some very few words, that is, you take the M matrix, right? M matrix, you have this words, all this cricket, what we showed, no? Bat, inning, season, game, etc. And you see there's a large fraction of the probability mass is sitting on those words. That is, these numbers are very high. Okay? In such a case, we can provably show that the keyword search will be outperformed by this. And that was a great explanation. And of course, there's many math here, right? So essentially, this gives a very interesting idea. So then topic is nothing but a probability distribution over words. This is the first time this sense came out. Right? So what is the document now? So document is nothing but maybe I am rolling a dice with D number of faces, where D is the vocabulary, M draws, you know. And each time a word shows up, I just put it in document. So under that model, and all this was, like all this is true. So I have 8 minutes, so let me speed up. So sorry. Now the question is, this is 2000, right? People understood, great. But what is the assumption they made? They said each document has only one topic. That was the assumption, right? We flashed one slide. Each document is about one topic, right? That is, each draw is from one distribution. Now the question became is that, okay, so now here is a paper. You know, this is about art and computer science. Obviously, this LSI is not going to work here. So people have, as people got, as we were trying to apply LSI, they quickly found out that, okay, this is breaking down in these places. So we need to have models which can go beyond that, which can handle multiple topics in a single document. So for example, let's not get political here, but let's say there's a document. We are talking about Arun Jaitley. We are talking about Chidambaram. We are talking about BCCI. See, they are both on the BCCI board. We're talking about corruption here. So this document, this is a document which comes out. Right? This is about BCCI scandal. See, but here they are not on the opposing sides. Correct? So it's about cricket, it's about politics, it's also about corruption, right? So LSI will not be able to handle this. Correct? So now what do we do? So this is a very interesting open question. And now in came a very fantastic answer in 2002, where they actually took the idea of probabilistic, that the topic is a probability, and they tried to fit actually a full generative model of a document. I mean, a very complex model. I will not have time because I'm racing against that. It's 5 minutes. So we'll just say that LDA is a great tool, but it's a pretty probabilistic, okay? So here's a tool, and here's what LDA can do. So they built a model of science, that is, they've taken the Science magazine over the last 100 years. They just took this on the data set, they ran this model. So it's discovering, so they tracked how those topics will change. So for example, you see 1960, it's a sea, water, fish, marine, oceans. What is it? Something to marine science, right? Some marine biology. So how that topic has evolved, just to give you another example, how you can visualize, large document collection. So I won't spend much time on this. So essentially, the idea is this. So the main idea was that, okay, LSI, great tool, but it can only handle one topic per document. And we say we have a new tool which can do multiple things. So what does it do? It says that, okay, for example, assume there are only 2 words in a topic, just to have a visualization. So let us put some weights on these. So you can find out that, suppose there are 3 topics. So you can put it as a triangle. And now what it is doing is, what the LDA new topic is doing is putting some weights here, putting some weight there, and putting some weight there. And trying to add a linear combination of them. That is, it's trying to find out a point inside the triangle. And that's a new distribution now. And now they're drawing documents according to that distribution. Okay? So that usually gives them the idea of the flexibility to handle multiple topics per document. Okay? So obviously, on the flip side, great to explain. But from a theoretical computer science, it's nightmare. Everything is NP hard. Everything in the sense that, okay, I give you a document, tell me which topics are there, NP hard. How will I find topics from a large document corpora, NP hard. Okay, but these guys who designed it, so they gave MCMC techniques, Markov-Chain Monte Carlo techniques, which doesn't have guarantees but works fabulously well. And this is by far now is the industry standard. I mean, this has been used heavily, David's code. So of late is that, so given the importance of this, so of late there's been interest in understanding that, okay, can we do better? Can we develop algorithms where we can guarantee that if there's a topic, I'll find it, and will not be stuck by this NP-hard assumption, right? So that is this recent interest, and that's where our results were. So basically what is the recent last 2-3 years this is happening. So basically, as we now saw, that M is a matrix, each column is a topic, and you're putting weights on them, right? And the weights are random. So given an M matrix, you're randomly putting weights on them. You generate a new distribution. For distribution, you generate a document. This you do it many, many times. Remember, each time the weights are changing, right? But if I show you enough documents, M is not changing, right? So probably I can still be able to guess M. So that's the main idea, right? So now, often this is not always possible until you make assumptions on M. So I will quickly point out. So this is a breakthrough paper, a phenomenal breakthrough. What they said was that, okay, if you assume that an M matrix, right? each column of M. Column means there's a word, right? If there is a word which occurs in no other topic, but occurs only on that topic. For example, if you see there's a word bat happening, and bat can only mean, of course, forget the animal, but say bat only happens if I'm looking at only sports, let's say. So if I see the word bat, it must mean cricket. So the probability of occurring of bat occurring in any other topics is 0, right? So you can use that to anchor. This is like a signature word. If the moment I see this, I know cricket has occurred. That particular topic has occurred, right? So using that and some clever mathematical tools, this Aurora and all that gave a fabulous algorithm which has this kind of sample complexity. Now, thing to notice, so they conjectured that you have to go beyond SVD, right? Because LSI was SVD. It can only do one topic, right? Remember, LSI was SVD based, you can only do one topic, right? So they argued that, okay, we have to do other things and all that going beyond SVD. Now I have exactly 1 minute, so I'll tell you our result. So, a few minutes more? Okay. I'm not sure the audience will like it, but, okay. So let's see, let's put the result and then we'll take some questions. So our result is, we'll make some assumptions, we'll not tell you what. But assumptions are weaker than the previous ones. What we suggest is do some thresholding, do SVD, and I can beat your sample complexity. And that's our result. So if you want to hear that, we're happy to talk about for another 20, 30 minutes. And I think I'll stop here and take questions. Yes?
Hi, I'm Venkatesh from IIIT Delhi.
Sure.
So I've been studying these topic models, and it's interesting that we can use co-occurrence and try to figure out some semantic value out of the documents. And as you say, it's quite reasonable that it helps in search and other kind of applications. But I wonder how interesting are these topics, and how do you make these topics interesting? Ultimately, there is a manual intervention for labeling these topics, right? So you have these 5 words, and from that you said it's either baseball or cricket or whatever, right? So systems may not come up with such interesting topics. It might just find another term which is not so interesting for labeling that topic. What do you do?
So your question is that if I run it on a general corpora, I may not get good topics per se. So topic modeling has issues. One of the issues is that currently that if I do not set the number of topics correct, I may get topics which have garbled words. Okay, so some amount of hand tuning is needed to that effect. So we are not there the full, the whole things, and so this is clearly a very evolving research area. But the interesting point is the example which I showed, 2 examples I showed, Wikipedia and Science. Proven examples on large document collection, it is giving good results. Right? So which basically means that if you randomly take some, collection of documents, I may not be able to find out the topics may not become coherent. Okay, but probably if the documents have some link, there are indeed some topics, right? The LDM model, does discover some things, and for example, now the new results, the Aurora result or our result, now are trying to can tell you more precisely that if the document has these characteristics, we can be able to find them. So that's happening. So clearly this is going to be dominating the field for some time now.
Thanks.
Right. Yeah, I can hear you.
Just a small question.
Sure.
You said about your result that you use some kind of thresholding followed
Yes.
by SVD.
Yes.
Do you mean thresholding on the columns of that matrix or something?
So what you do is, data is A matrix, right? Data will be given to us as A matrix. From that I have to do whatever I have to do. Node will give me M, right? So what we do is I take the A matrix and do some thresholding operation. Remember the LSI, original LSI was you factorize the A matrix by SVD. And that took them where they took them, right? So now we are just suggesting, under some assumptions, that you threshold the A matrix, then apply SVD, then also do have to do some k-means clustering, and it gives me the M matrix.
Is there any intuition why this
Okay,
works?
so intuition is another 10 minutes. So basically, okay, the idea is, okay, let me spend that, since Satish said I can take some more time. So we make this interesting assumption, which we differ. So first thing to note is, Satish, I'm okay, can I take a few more minutes? Okay, okay. So let me bore you with some details. So you see, so here is an interesting parameter called P naught. P naught is what they said is that the word bat, the probability of the word bat occurring, and the word bat occurs only in that particular topic and anywhere else, right? So it's P0 to the power 6 is the denominator. That's what Arora's result is. S is number of samples I need to recover an M hat, which is very epsilon close to the original topic matrix, right? So this is a horrible thing, right? Sort of. Okay. So now we make a sort of a different assumption. So the assumption we make is as follows, and it is in line with the LSI assumption. What we assume is, maybe the BCCI example is a good topic, good document to think about. It may have politics, it may have corruption, it may have cricket administration, but fundamentally it must be about cricket. And this topic should dominate it, right? So we say that, okay, let's think about those document corpuses where there will be multiple themes. And so when I use the word theme is basically what we're calling as topics. So document have multiple themes, but one theme will dominate. Okay, this is the assumption I make on the corpus. That is, the weight on that particular theme will be very high. Okay? Now if you see, if I push it to the extreme, I recover LSI, right? Okay? LSI was that only one topic occurs. Weights for the rest are 0, isn't it? So I make it high. Not to 1. Since I can't make it to 1, the math is very difficult, and but the essential idea is that is where the thresholding helps me in discovering those dominant topics. So that's the intuition. If that, okay.
Okay, so let's thank Chiru.
Thank you.